Morning, students. Okay, in the last class we discussed about the correlation, correlation or cross correlation and autocorrelation we discussed, and these properties also we discussed. Cross correlation means we are comparing the signal with another signal. X1 of t will be compared with X2 of t, right? So autocorrelation means the signal is compared with itself only. That is called autocorrelation. Okay, then we will see. We saw the relation between correlation and the convolution. Okay, and then properties of autocorrelation and cross correlation functions. Okay, now we will do some problems. See the problem. Find the cross correlation between u of t minus u of t minus tau and e of minus t into u of t. Here, two different functions are given. This is x1 of t and this is x2 of t. x1 of t is u of t minus u of t minus tau. x2 of t is e of minus t into u of t, right? So here x1 of t is this one, x2 of t is this one. So cross correlation between x1 of t and x2 of t is denoted by j12 of tau. So j12 of tau is equal to x1 of t converted with x2 of t. Right? Fourier transform of x1 of t is x1 of omega, and Fourier transform of x2 of t is x2 of omega. So x1 of t converted with x2 of t will become simple multiplication in frequency domain. Okay, x1 of omega into x2 of omega. So see, x1 of t is this one. We will find out Fourier transform of this one. In the same manner, we will find out the Fourier transform of these two. By multiplying these two, we will get the cross correlation of these two signals, right? Okay. See, f1 of x1 of t is equal to f of u of t minus u of t minus tau, and x1 of omega is f of u of t minus f of u of t minus tau, right? So u of t, the Fourier transform of unit step function u of t is pi into delta of omega plus 1 by j omega. Similarly, using time shifting property of Fourier transform u of t minus tau, Fourier transform of u of t minus tau will become e power minus j omega tau into u of omega. So right, u of t omega is equal to e of e power minus j omega tau into already u of omega is pi into delta of omega plus 1 by j omega, right? So j1 of tau equal to x1 of omega into x2 of omega. What is x1 of omega? X1 of omega is pi into delta of omega plus 1 by j omega minus e power minus j omega tau into pi into delta of omega plus 1 by j omega whole into minus 1 by 1 plus j e power minus t into u of t is e power minus t into u of t is minus 1 by 1 plus j omega. So multiplying these two, so that we will get pi into delta of omega plus 1 by j omega into e power minus j omega tau into pi into delta of omega plus 1 by j omega, right? Right? So it is equal to j12 of tau is equal to e power minus j omega tau into pi of delta pi into delta of omega plus 1 by j omega whole square, right? So next we'll see the detection of periodic signals in the presence of noise by correlation. How to detect the periodic signals even though noise is present by correlation. Using correlation, we can detect the periodic signals, including noise. Okay, so correlation technique provides a powerful tool in the solution of the above problem. So using correlation, we can detect the periodic signal with respect to periodic signal in the presence of noise also. Okay, we shall consider the application of both autocorrelation and cross correlation in the detection of a periodic signal in the presence of noise. So the noise signal in practice is a signal with a random amplitude variations, is it not? So noise is nothing but it doesn't have any constant amplitude. It has some random amplitude. Okay, random amplitude variations. Okay, if R of t, if this is S of t, if S of t is a periodic signal and N of t is the noise signal, then limit t tends to infinity 1 by t into integral minus t by 2 to plus t by 2 s of t into n of t minus tau dt is equal to 0 for all values of tau, right? So if s of t is a periodic signal and n of t is the noise signal, then limit t tends to infinity 1 by t into integral minus t by 2 to plus t by 2 s of t into n of t minus tau dt is equal to for all values of tau. If we denote chi Sn of tau as the cross correlation function of s of t and n of t, then chi Sn of tau is equal to 0. Chi Sn of tau equal to 0, right? So detection by autocorrelation. First of all, we see the detection by autocorrelation. Let S of t be a periodic signal mixed with a noise signal N of t. Then the received signal is F of t. S of t equal to mixing of these two, that is S of t plus N of t. Let J ff of tau, J ss of tau, and J nn of tau denotes the autocorrelation functions of F of t, S of t, and N of t respectively. Then chi ff of tau is equal to limit t tends to infinity 1 by t into integral minus t by 2 to plus t by 2 f of t into f of t minus tau dt, right? Or it is equal to limit t tends to infinity 1 by t into integral minus t by 2 to plus t by 2 s of t. F of t is nothing but combination of s of t and n of t, s of t plus n of t into s of t minus tau plus n of t minus tau dt, right? So this is nothing but by multiplying this one, we will get chi ss of tau plus chi nn of tau plus chi sn of tau plus chi ns of tau. Since the periodic signal s of t and noise signal n of t are uncorrelated, here s of t and n of t are uncorrelated, then chi sn of tau is equal to chi ns of tau, both are equal to 0. Okay, so then it will become chi ff of tau is equal to chi ss of tau plus chi nn of tau. Here chi ss of tau is a periodic signal and chi nn of tau is a non-periodic signal, right? S of t is a periodic signal, n of t is a non-periodic signal, right? The autocorrelation function of a periodic signal masked by noise is as shown as, see, first of all we will take chi, this is a chi ss of tau. It will be masked by the noise signal chi nn of tau. Then we will get chi ff of tau as this is the decline signal is chi ff of tau, right? Autocorrelation function of periodic signal masked by noise. So here chi ss of tau dotted line signal is chi ss of tau signal. This will be masked by this signal chi nn of tau. Then finally we will get the plane signal as chi ff of tau. This is autocorrelation function of the periodic signal masked by noise. Okay. Next, we will see the detection by cross correlation. Before we will see the so far we will see the detection by autocorrelation. Now we will see the detection by cross correlation. So f of t, as we already know that f of t is a combination of s of t and n of t. So chi fc of fc of tau is equal to limit t tends to infinity 1 by t into integral minus t by 2 to plus t by 2 f of t into c of t minus tau dt. But f of t is combination of s of t and n of t. That's why we can write s of t plus n of t into c of t minus tau dt. Okay. Now it is equal to s of t into c of t minus tau dt plus n of t into c of t minus tau dt. That will be written as chi sc of tau plus chi nc of tau. C of t is a periodic function, is uncorrelated with random noise signal n of t, hence chi nc of tau equal to 0. Therefore chi fc of tau is equal to chi sc of tau. Since s of t and c of t are signals of same frequency, it follows that chi sc of tau is also a periodic function of the same frequency. Okay, so it is evident that if the cross correlation of the contaminated signal f of t with c of t is a periodic signal, f of t must contain a periodic components of the same frequency as that of c of t, right? Basically f of t is mixed with a periodic signal and a noise signal, right? Which is f of t, c of t yields a periodic signal f of t must contain a periodic component of the same frequency as that of c of t. This is detection by cross correlation. Okay, next we will see the extraction of a signal from noise by filtering. One is a correlation technique. By using correlation technique, we can detect a periodic signal in the presence of noise. And another way is extraction of a signal from noise by filtering. A signal masked by noise can be detected by correlation technique or by filtering. Okay, this is another technique. Okay, these two techniques are equivalent. This filtering technique and correlation technique both are equivalent. So correlation technique is means of extraction of a given signal in the time domain, whereas filtering is exactly same result in the frequency domain. Only difference is this one. Okay, so we'll extract a periodic signal from noise. In time domain is nothing but correlation technique, and filtering technique is nothing but we'll extract a periodic signal from noise in frequency domain, right? So relation between correlation and filtering. So consider the two arbitrary signals f1 of t and f2 of t. The cross correlation function j12 of f is defined as suppose if you take the Fourier transform of f1 of t is f1 of omega and Fourier transform of f2 of t is f2 of omega, then Fourier transform of j12 of tau is nothing but f1 of omega into f2 of minus omega, right? So cross correlation in the time domain and frequency domain is as follows. Figure A is nothing but cross correlation in time domain, whereas figure B is nothing but cross correlation in frequency domain, right? So here f1 of t and f2 of t is its response is j12 of tau. Okay, here f1 of t, the Fourier transform of f1 of t is f1 of omega, and f2 of t is f2 of minus omega. So j12 of tau is nothing but multiplication. In frequency domain, it will become multiplication. So f1 of omega into f2 of minus omega. So this is the impulse response h of t of the system with a transfer function f2 of minus omega is given by h of t is inverse Fourier transform of f2 of minus omega. Okay, so but f2 of t, Fourier transform of f2 of t is f2 of omega, and Fourier transform of f2 of minus t is f2 of minus omega, and h of t is f2 of minus t. So this result can now be applied to the problem of the detection of a periodic signal from a random noise signal. Let S of t and N of t are the periodic component and random noise components respectively. S of t is the periodic component and N of t is the random noise component. Then the received signal f of t is nothing but a combination of the periodic signal as well as the noise signal. So it can be written as f of t equal to S of t plus N of t, right? S of t plus N of t. The periodic component S of t present in f of t can be detected by cross-correlating f of t with another periodic signal c of t of the same period as that of S of t. So we need a system which has unit impulse response c of minus t or which has a transfer function c of minus omega, where the Fourier transform c of t is c of omega and Fourier transform of c of minus t is c of minus omega. Here, C of t is a periodic signal of period t naught, and C of omega is the Fourier transform of C of t, will consisting of impulses located at omega equal to 0 plus or minus omega naught plus or minus 2 omega naught up to plus or minus n omega naught, where omega naught equal to 2 pi by t naught or 2 pi f naught. These impulses have magnitudes equal to 2 pi times the corresponding coefficients of the exponential Fourier series for C of minus t. Thus, if C of t is expanded by Fourier series, then C of t can be represented as sigma n equal minus infinity to infinity Cn into e power plus jn omega naught t, where omega naught equal to 2 pi by t naught. Then transfer function C of omega of C of t is given by C of omega is equal to 2 pi into sigma n Cn into delta of omega minus n omega naught. Since C of minus omega equal to complex conjugate C star of omega, then C of minus omega equal to 2 pi into sigma n Cn star of delta of Cn star into delta of omega minus n omega naught. Thus, C of minus omega consists of impulses located at omega equal to 0 plus or minus omega naught plus or minus 2 omega naught, etc. So C of minus omega represents a system which attenuates all the frequencies except omega equal to 0 plus or minus omega naught plus or minus 2 omega naught up to plus or minus m omega naught, etc. Now let us consider C of t to be a sinusoidal signal cos omega naught t, and let the cross correlation be performed over a finite interval minus t to minus t naught to 0, which is as shown as C of t minus t naught to minus t to 0 like this. This is C of t. So C of minus t is its mirror image. So this is varying from 0 to t. So C of omega spectrum is like this. Omega naught, which is the spectrum minus omega naught to plus omega naught, can be represented like this. Okay, C of t is its original signal, its mirror image, and its spectrum will be represented like this. The Fourier transform of C of minus t is a sampling function shifted by plus or minus omega naught. So figure C is the magnitude function. The frequency spectrum or amplitude spectrum or magnitude function is like this. Okay, that is about the cross correlation and extraction of a signal from noise by filtering. So filtering technique is used in frequency domain and correlation technique is used in time domain. Okay. We are going to discuss about the sampling theorem. What is meant by sampling theorem? Generally, you can say that the continuous time signal can be represented by as a discrete time signal. That is nothing but the sampling. It is the process of converting a continuous time signal into discrete time signal. That process is called sampling process. Sampling process is the process of converting a continuous time signal that is represented by CT signal into discrete time signal. What is meant by discrete time signal? Discrete time signal means a sample of continuous time signal can be frozen for some time and it can be divided into equal intervals of the time. A sample of continuous time signal can be frozen for some time and it can be divided into equal intervals of time so that we can get the discrete time signal. Okay. After sampling, the signal is defined at discrete instance of time. The signal is defined at discrete instance of time, and the time interval between two subsequent sampling instants is called sampling interval. Okay, after sampling, the signal is defined at discrete instance of time. Signal is defined at discrete instance of time, and the time interval between two subsequent sampling instants is called sampling interval. Sampling interval, right? So here one of the important factors is the signal sampling rate must be kept sufficiently high. So this is the important factor. So which is signal sampling rate must be kept sufficiently high so that the original signal can be reconstructed from its samples. So by keeping the signal sampling rate must be high, so the original signal can be reconstructed from its samples. It is represented diagrammatically as C. This is x of t given to the system having the frequency f of s equal to 1 by t. Okay, if it is on, then we will get x of n equal to x of n t. Okay, this is a multiplier. So x of t is the input signal. X of n t is nothing but sample sequence of x of t. X of n t is nothing but this is sample sequence. It will be represented like this. So x of t must be multiplied with delta t of t. Delta t of t. Then we can get x of n t. That is a sample sequence. Sample sequence of x of t is like this. X of n t. This is a this figure represents the sampling operation, where capital T is nothing but time interval between successive samples, and the sampling frequency is given by Fs is equal to 1 by T Hz. Okay, 1 by T Hz. Another way of representing the discrete time signal is xs of t is equal to x of t multiplied by delta t of t, where delta t of t is nothing but sigma n equal to minus infinity to infinity delta of t minus nt. That is equation number 2. That is the function xs of t is the product of x of t and the train of impulses. Train of impulses. So therefore xs of t is equal to sigma n is minus infinity to infinity x of nt into delta of t minus nt. That is considered as equation number 3. Applying Fourier transform to equation number 3. Okay, applying Fourier transform to equation number 3, we get Fourier transform of xs of t is equal to Fourier transform sigma n equal minus infinity to infinity x of nt into delta of t minus nt. Or we can write this as sigma n equal to minus infinity to infinity x of nt into Fourier transform of delta of t minus nt. We have Fourier transform, that is equation number 4, and we have Fourier transform delta of t minus nt is equal to integral minus infinity infinity delta of t minus nt into e power minus j omega t t, right? This can be written as e power minus j omega n t, j omega n t, that will be considered as equation number 5. Okay, therefore x of e power j omega, that is Fourier transform of xs of t, is equal to sigma n equal to minus infinity infinity x of nt into e power minus j omega nt, j omega nt. Sigma n equal minus infinity infinity x of nt into e power minus j omega nt, that is equation number 6. But we know that delta t of t is equal to the train of impulses, that is sigma n equal minus infinity infinity delta of t minus nt. So we can write this as 1 by t into sigma m equal to minus infinity to infinity e power jm rho naught t. Okay, e power jm rho naught t, that is equation number 7, where rho naught is 2 pi by t or omega naught. You can say that omega omega naught t, omega naught equal to 2 pi by t. Okay, so we can write this as xs of t is equal to x of t into 1 by delta t of t, that is 1 by t into sigma m is minus infinity infinity e power jm omega naught t, or we can write this as 1 by t into sigma m equal to minus infinity infinity x of t into e power jm omega naught t, that is we considered as equation number 8. So Fourier transform of xs of t is equal to 1 by t into sigma m equal to minus infinity to infinity Fourier transform of x of t into e power jm omega naught t, right? That is equation number 9. If a Fourier transform of x of t is x of j omega, then Fourier transform of x of t into e power jm omega naught t is equal to frequency shifting property, that is x of j omega minus m omega naught. So by substituting equation number 10 in equation number 9, we get f Fourier transform of xs of t is equal to 1 by t into sigma m is minus infinity infinity x of j omega minus m omega naught, right? That is equation number 11. So it is equal to 1 by t into sigma m is minus infinity to infinity x of j omega minus 2 pi m by t, where omega naught equal to 2 pi by t. That is equation number 12. Thus, the Fourier transform of the sampled signal is given by an infinite sum of shifted replicas of the Fourier transform of the original signal. So, an infinite sum of shifted replicas. So, these are the shifted replicas of the Fourier transform of the original signal. So, Fourier transform of excess of t is nothing but excess of t is nothing but 1 by t times sigma m is minus infinity to infinity x of j into omega minus 2 pi m by t. So Fourier transform of the sample signal is given by an infinite sum of, this is an infinite sum of shifted replicas of the Fourier transform of the original signal. Now consider the signal x of t is band limited to fm. It is limited to fm. So that is the highest frequency component of x of t is Fm, then x of j omega is equal to 0 for mod omega is greater than omega m, where omega is equal to 2 pi into Fm, that is equation number 13. So it can be represented diagrammatically as x of j omega is like this. Uh, it is band limited to Fm, that is minus omega m to plus omega m. That is a frequency spectrum of continuous time signal. Excess of j omega is nothing but frequency spectrum of x of mt with pi by t equal to omega m. Here pi by t is omega m. Okay, so it is like this 1 by t excess of j omega like this. And third one is the frequency spectrum of x of nt with pi by t is greater than omega m. If it is greater than omega n, it will be represented like this. Next, the frequency spectrum of x of nt with pi by t is less than omega n. So there may be overlapping of the samples. Here, aliasing occurs in the above diagram. We can prevent the aliasing error if the highest frequency component omega m in the signal x of t is less than or equal to pi by t. That is pi by t is greater than or equal to omega m. If Fs is equal to 1 by t, then pi into Fs is equal to pi into Fs is equal to omega is greater than or equal to omega n. Okay, pi into Fs is greater than or equal to omega n, or pi Fs equal to 2 pi into Fm. Fs is greater than or equal to 2 Fm. Okay, that is equation number 40. So finally, the sampling theorem is defined as a band limited signal x of t with x of j omega equal to 0 for mod omega is greater than omega m is uniquely determined from its samples x of mt if the sampling frequency fs is greater than or equal to 2 fm, that is sampling frequency, fs is sampling frequency, must be at least twice the highest frequency present in the signal. Okay. That is the definition of the sampling theorem. The band limited signal x of t with x of j omega is equal to 0 for mod omega is greater than omega m is uniquely determined from its samples x of nt if the sampling frequency fs is greater than or equal to 2 fm, that is sampling frequency must be at least twice the highest frequency present in the signal. That is the actual definition of the sampling theorem. Okay, with this, I'm concluding the today's class. Tomorrow we'll discuss about the Nyquist rate. Okay, thank you.